There are three kinds of parasequences: progradational parasequence, aggradational parasequence and retrogradational parasequence. In case of a progradational parasequence, each successive parasequence going up through the set shows shallower water phases. This is the example of progradational parasequence. In this case, sediment input is more than accommodation, sediments coming from this side. In all these three diagrams, this is the seaward direction or the basinward direction, and this side is the landward direction. Here a brown color is found, then a yellow color which continues, but over that is a yellow dotted region. What is an aggradational parasequence? Here all the individual parasequences show the same cycles of phases with no overall trend of shallowing or deepening. This is a case when sediment input is equal to accommodation. Therefore, there is a vertical stacking up, and as I go vertically up in so many directions, similar lithologies are found. In this case, sediment input is equal to sediment accommodation, that helps in developing similar phases vertically upward. Let us take the retrogradational parasequence. These are made of parasequences that show a trend of becoming deeper up through the succession, that is, the top bed of the higher parasequence is a deeper water phases. Let us see. This is the retrogradational parasequence. This is a case when the sediment input is less than the accommodation, and in this case we can note that how the phases are shifting towards the landward direction. In these cases, if we note the shift of this yellow dotted rock, here it is towards the seaward direction, whereas in the retrogradational parasequence they are towards the landward direction. So, if you do a vertical succession here, what comes out? As you are going upward, you are getting the deeper water phases over here. This is what is said, the top bed of the higher parasequence is a deeper water phases. Now, under what condition these three kinds of parasequences can be produced? Let us recollect a high stand system tract. This is the example of a high stand system tract when the water level is increasing. Under such a situation, aggradational to progradational trends will be produced within the parasequence. So, these two are indicative of high stand systems tract. On the other hand, a transgressive systems tract is characterized by parasequence sets with a retrogradational trend. Let us recollect what is a transgressive systems tract. Here is the example of a transgressive systems tract when the transgression is happening, and this would be the product TST or the transgressive systems tract. So, this curve in its different portions can be correlated with these kinds of sedimentation. Consider a case of a falling stage systems tract given by FSST. This is the falling stage systems tract. Here what happens? The parasequences are not stacked vertically, but are instead arranged laterally. In this case, we do not see a vertical up succession in case of an FSST. Now, here two patterns can be discriminated: rate of sea level fall in relation to the rate of sediment supply. Suppose with a high sedimentation rate or slow sea level fall, then the individual parasequences are stacked against each other to form an attached falling stage systems tract. This is the one. But if there is a faster sea level fall and or lower sediment supply, then it leads to a detached falling stage systems tract. Consider this is the ramp geometry, and from here sediment is coming. They will be deposited continuously in case there is a high sediment supply or there is a low rate of sea level fall. But a second case exists when the sea level is falling very rapidly or the sediment supply is very less. In that case, we do not get a continuous or attached falling stage systems tract. Deposition can be restricted in different zones. This is a crude diagram representing this statement. A question may come while considering these figures: how much is the thickness of these units? Say this depositional unit, how much is the thickness? They can be of the order of 100 meters or more. Let us take the carbonate sequence stratigraphy. There is a difference between the clastic sedimentation and a non-clastic sedimentation. In a clastic depositional system, the sediment supply is mainly detritus coming from the hinterland area, supplemented at times by the erosion and reworking of the materials from the shelf. In contrast, the supply of materials in carbonate setting is governed mainly by the factors that control the biogenic productivity. In case of carbonate deposition, biogenic productivity is the main point. And here the important factors are water temperature, salinity, nutrient supply, suspended sediment content, water depth, and the area of the shelf that is available for production. Variations in relative sea level determine both the water depth and the shelf area. So, there is a direct link between relative sea level and sediment supply in carbonate depositional systems. We are going to see now the pattern of strata in a carbonate rimmed shelf during cycles of relative sea level rise and fall in this figure. We are going to consider a high stand, a falling stage, and the corresponding high stand systems tract, sequence boundary, respectively low stand and the corresponding low stand systems tract, transgression and high stand and its corresponding transgressive systems tract and high stand systems tract. Production of carbonates is greatest at the shallow water, and that is why shallow carbonate deposition is indicated here by the green color. As one goes in the deeper water, we find pelagic deposition. In between the shallow carbonate deposition and the pelagic deposition lies the reef and shoal deposition of on shelf edge and followed by the slope deposits. And the shallow marine carbonate facies, here the term facies is used, that extends out of the shelf edge and extend down the slope. So, this is the domain of the shallow marine carbonate facies. Now, in this diagram the sea level was up to this and that is the water level is. Now, from that position there is a fall in the water level. So, the shelf karst formation get exposed. The ramp carbonate sediments can normally be recognized here by the presence of solution and karstification, soil development and or subaerial evaporite formation. Now, we are going to see the low stand systems tract. In this case, fall of the sea level below the shelf edge dramatically reduces the area of carbonate factory to a small patch on the slope. So, the sea level has further fallen down and the place where earlier carbonate production was happening is greatly reduced. Transgressive systems tract. Here again the sea level rises. Now, the shelf is drowned at the onset of the TST. So, what was karst here can get submerged and then again shallow carbonate deposition can take place. Let us comment about the carbonate ramps. These ramps are generally areas of lower carbonate productivity. If a TST is developed, then it consists of retrogradational parasequence sets. How the carbonate parasequence is characterized? They typically can consist of beds deposited in the lower subtidal zone consisting of wake stones that coarsen up into pack stones and then to grain stones deposited in the high energy wave reworked zone of shallower water. This becomes the succession as the coarsening takes place in this direction. That is what is said here. And a thickness difference can be noted in case of carbonate involved in sequence stratigraphy. Parasequences that form a part of the retrogradational or aggradational package tend to be thicker with respect to what? they are thicker with respect to the progradational parasequences. In other words, the progradational parasequences involving carbonates are thinner than the retrogradational or aggradational packages. Where are the sequence stratigraphy applied? It can be applied on the graphic sedimentary logs. It can also be used for borehole core and wireline log data and with seismic reflection profiles. The sequence stratigraphic study analysis of seismic sections is of great importance. Here is a summary of the stratal geometries and the pattern within systems tract in the depositional sequence. The maximum flooding surface, the condensed facies have been pointed out here. The high stand systems tract coming from the characterized by the progradational parasequences can be observed. The high stand systems tract can be observed. The sequence boundaries can be identified and the transgressive systems tract indicated by the retrogradational parasequence can also be identified. Finally, the low stand systems tract, the submarine fan turbidites can be found within the basin. Sequence stratigraphy study must start with facies analysis throughout the available rock sections with the aim to find out the relative sea level change. This is the beginning point of work on sequence stratigraphy. So, what to study? The lithology, sedimentary structures and the biogenic features that can talk about the depth at which the rock was formed. The shallowing up pattern can identify the parasequences. The flooding surface can be recognized by relatively abrupt change from shallower to deeper water facies. Suppose in a vertical section we have found the shallower water facies and over that the deeper water facies and the variation is abrupt, then it can indicate a flooding surface FS. Finally, the whole succession can be divided into systems tract and depositional sequences. So, here is a graphic presentation, the sequence boundaries identified, then the low stand systems tract, then the foreshore, then the shore face, transgressive systems tract, offshore transition and then maximum flooding surface, then offshore transition, shore face and the high stand systems tract. So, starting from almost like saying low stand systems tract, passing through transgressive systems tract, passing through maximum flooding surface and then the high stand systems tract can be recognized in the succession. And from here I am requesting students link this diagram with the sea level rise fall curve with respect to time. How we can use the petrophysical logs in the sequence stratigraphic analysis? Through the petrophysical logging tools, we can assess the relative proportions of sand and mud within the succession. So, if this ratio sandier portion of rock indicates shallower maiden deposition, decreasing values upward on a gamma ray log can therefore be taken to indicate the increase in the sand content. And conversely, if the gamma ray log value increases, that means increase in the mud content. And if this increase is abrupt, such an increase, if abrupt, means that an evidence of a flooding surface. Based on the sand mud ratio that we deduce from the gamma ray log, it is possible to identify patterns of progradation, retrogradation and aggradation. There is another way of identifying the flooding surface, and this can be done in spectral gamma logs by noting increase in the potassium content or in certain concentration of glauconites. Glauconite is a green mica usually produced in the shallow marine environment. Imaging tools, the image logs can be used to interpret the geology, and in one of my earlier NPTEL lecture I have explained how it can be done. How do we perform correlation of sections using sequence stratigraphic principles? This part is most important. We can link progradation pattern at one place with progression pattern in another place, even though the lithologies can be different. So, this means what? We are essentially differentiating such processes from lithostratigraphy. The same holds true for the fossils. Biostratigraphically, P1 and P2 may be different, nevertheless, a sequence stratigraphic correlation can be made. So, we can write this is not following lithostratigraphic principles nor the biostratigraphic one. That is interesting. The maximum flooding surfaces may be traced by identifying evidence of sediment starvation on the outer parts of the shelf and change from retrogradation to progression pattern near shore. The maximum flooding surface can be correlated. Consider a hypothetical example of correlation between logs in different parts of the coastal and marine environment. This log comes from this area, this log comes from this area, this log comes from this shallow sea area, this one comes from the much deeper area. Since this one is coming from much deeper area, most of the sediments are submarine fans and pelagic deposits, and because of their difference in locations 1, 2, 3 and 4, lithology wise we find a difference as well. Now, even though the exact lithology here and the exact lithology here can vary, one observes in these two sections the maximum flooding surface can be tracked in the offshore region. This is the advantage of studying the sequence stratigraphy. In our study of sequence stratigraphy and the correlation, we can also predict what we are expecting in the new sections. In location 1, when the estuary condition existed, in location 2 it can be the foreshore, and in location 3 it can be the shore face. Similarly, you can watch fluvial here, estuary there, foreshore there, shore face here, offshore transition over there. They can be correlated. What leads to the sea level fluctuation is a fundamental question in geoscience. We have referred that uplift and subsidence as the reasons of sea level fluctuation, but note that they cannot be on a global scale. Every part in the world cannot be moved up or going down, so that everywhere a transgression or everywhere in the world a regression is unlikely. But there are aspects of plate tectonics where on a global scale sea level change is possible.